it works. So, thank you all. Thanks for giving me the opportunity to speak. My talk will be a short one and very humble in its goals because I will only define a certain family of objects and try to convince you that they're interesting and worthy of study. And that is everything I'm going to do. So, the objects in question will be the generalized Schubert varieties, but to properly define them, I will have to start with a slightly involved introduction about the chowering of the Grassmannian. So thanks to Matej's talk, you already know what chowerings are, so I don't have to spend any time saying what they are. And I would just be interested in particular in the chowerings of Grassmannians. So, as I'm sure you all know, I can start with a vector space of some finite dimension and look at some k-dimensional subspaces. And it is customary to write them using matrices that are, they are k by n. So by this, I will just mean the space, which is the row span of this. And of course, this notation is not unique. It is unique only up to row operations, and not any matrix that I can randomly write will give me a valid point. Only those that are have maximal rank, i.e. rank k, which is equivalent to at least one of the possible k by k minors being non-zero. And one thing that I might interest myself in is asking which of these minors are the non-zero ones, because maybe for a random matrix it might be all of them, but for special matrices, not all of them. To talk about these minors, let me label them with partitions. So a partition for me is just a finite sequence that is weakly decreasing of non-negative integers. And here for me, I will always use them with some fixed length, so I will just possibly pad them with zeros, and that's okay. And if I have a partition lambda like this, I will use it to denote that minor, which is composed of columns that have indices lambda I plus I. So you can imagine it as like a partition of all zeros is just the first minor, just the first k columns, and these lambdas tell me how much I should shift each column. And when I have this, I will define Schubert cells and Schubert varieties. So a Schubert cell will be some kind of probably open set, where I say this is the set where where basically the lambdath minor is the first non-zero one. And I mean first in the sense of there is no previous minor which is non-zero, and by previous I mean just component-wise comparison. And then I will say that the actual Schubert variety is the closure of this. And I could also characterize it by some condition on minors, but I will mostly content myself to just say it's the closure of the Schubert cell. Okay, this is all very nice. Let's see an example. So the smallest Grassmannian that is actually really a Grassmannian, not some projective space. So let's take GR24, and in here we have 6 Schubert cells, and this is the Hasse diagram of how they're included in each other. So, for example, the 0,0 cell, sorry, I should be precise, the 0,0 Schubert variety is the whole Grassmannian, and every talk should have a typo. So this is the first one. This should be GR2, 4. This Schubert variety is just the whole Grassmannian, and the corresponding cell I can write it as those points in the Grassmannian where I just put the first k by k submatrix to just be the identity, and then I just put whatever in all of the others. And then there's other Schubert varieties. Some of them you may recognize as varieties that have their own names. There's a copy of a smaller Grassmannian in here, and there is also just a point in here. So it's this nice stratification. Going further, it actually turns out that these Schubert varieties form what's called an affine stratification. So that's some covering of my variety, the Grassmannian, by some affine patches that have some additional nice properties. I would rather skip the details, but it is very well known that if I have an affine stratification, these varieties, or rather their classes in the Chow ring, give me a basis of this ring. So in fact, the Schubert classes, which I will denote with these lowercase sigma lambdas, are a basis of the Chow ring. Great. And another thing that will be useful, that will bring some combinatorics into this, sorry?
Is this the result due to Tara?
Sorry?
Is this the one that's called the Tara's theorem? About the affine stratification doing this? The first two lines, I think so.
Yeah. I wouldn't know, but apparently so. Yes. I'm not familiar with the name, but it may well be so. So to bring some combinatorics into this, I will be using Young tableaus, as is customary, to write partitions. So this just means if I have something like this just tells me how many boxes I have in each row going from the top. And I have to warn you, I will abuse notation regularly in this talk. So sometimes I will just write sigma with a Young tableau in an index, and sometimes I will just forget the sigma altogether and just write the actual Young tableau to mean the Schubert cell, or sorry, the Schubert class in the Chow ring. So prepare for that. And there are some nice combinatorial interpretations of this. So for example, the number of boxes in a tableau tells me what's the codimension of my cell, or rather of my variety. I can read off when Schubert varieties are included in one another just based on when the tableaus, really as pictures, are included in one another. And I can also tell you that those Schubert varieties that appear in my given Grassmannian are exactly those tableaus that fit into a rectangle of size k by n minus k. So actually, this previous slide that I gave you like this, I can just repeat it, but this time with pictures. So it goes like this. This is, I think, very self-explanatory. Of course, the inclusion is opposite with respect compared to the inclusion of the actual pictures with boxes. So somehow the empty tableau is the whole Grassmannian. So far I've told you that these Schubert classes, they give a basis of the Chow ring, but of course it's a ring, so I should probably explain how the multiplication operation goes. And we are in a Chow ring, so by definition this multiplication is some kind of intersection, with the caveat that our objects, our elements are just some classes. So there are somehow some intersections of representatives under an assumption of transversality. But in this particular case of the Chow ring of Grassmannians, there is a combinatorial interpretation to just go with the Young tableaus. So I would like to be able to just multiply two of my basis elements. So I would somehow like to write this as a linear combination of other Schubert classes, and I would like to understand how do I get these coefficients wherever they are. Maybe just a first approximation, something I can say with absolute certainty, is that I know that the number of boxes in a tableau gives me the codimension of my varieties. So somehow it should be enough for me to run this sum just over those tableaus which have their number of boxes is how many mu has plus how many lambda has. So there is a grading on codimension / on the number of boxes in my tableaus. There is a combinatorial rule, and it has this, it's slightly famous, it's called the Littlewood-Richardson rule, but it's terribly complicated and unwieldy, and I hear there's some, basically folklore says that there have been several wrong proofs of it for many, many years before actually a correct proof appeared. In practice, it's usually much easier, less of a hassle to use a special case, which is called the Pieri rule, which tells me how to do this multiplication if one of the multiplicants is just a long tableau of several boxes. And in this case, this is just a sum over those tableaus where I've just added these k boxes to lambda, each in a different column. And I have to stay within this reference rectangle k by n minus k. So this will probably be clearer once I show you an example. So we may go like this. So I look in the Grassmannian GR37, which means that my reference rectangle is 3 times 4. And to make this, maybe I can even show this on the blackboard. So what tableaus did I actually pick? I hope I didn't make it too hard on myself. So we have this times this. And how I should think about it, I will draw sort of a next layer of possible boxes around this L shape. And well, the Pierre rule tells me I should just take a sum of all of those where I've just added 2 boxes somewhere in here. I should be careful. There's also this possibility. But I need to stay within the 3 by 4 rectangle. So somehow, yes. So somehow one possibility is that I add this box and this box, which is the first term on the right-hand side here. Alternatively, I might add this box, and that's how I get the other one. I might also forget this one and add these 2 ones in the middle, complete the rectangle like this, or I might take it like this. In general, if I was in a larger Grassmannian, I should also expect to get this, sort of a very long L, but this is outside the rectangle, so I don't take it. Yes, question?
2 boxes in between?
Where?
Like you have 2 imaginary boxes in between.
Where exactly?
Yeah, like on the right.
Yeah.
Top right. Those 2.
Yeah.
Those 2 are 2 imaginary boxes.
Yeah, there could, in general, there could be 2, but somehow in this case, there aren't because my reference rectangle forbids it. This one, so this one which would have 5 boxes at the top and 1 in the second row, this wouldn't actually be a valid Schubert class in this Grassmannian. Yeah. Sorry. Maybe that was confusing presentation on my part, but in general, there might be more. Right. Maybe I can even say a piece of intuition for why it's not that bad to forget General Littlewood-Richardson and just take Pierre, just remember Pierre. This is because these long one-row tableaus, they actually generate the Chow ring as an algebra. So somehow, if I understand how to multiply by these, I should be able to get by in an implementation sense. Yeah. So, are there any questions so far? If not, then I shall move on. Right. These combinatorial multiplication rules have some nice consequences. For example, here, if I just look at the multiplication between graded homogeneous parts of complementary dimensions, so somehow, if I go from codimension m pieces to dimension m pieces and multiply them, I should always arrive just in the homogeneous part that's just spanned by the class of a point. So this is just a copy of the integers, and these combinatorial rules, they imply that this is in fact a perfect pairing, and that Schubert classes are dual bases towards one another. So somehow what you should think about is maybe let me take an example. So let's say that I'm working with 2 by 3 tableaus, and somehow this tells me that the only thing that will give me anything non-zero in this graded part of points with respect to, let's say, this tableau is just whatever is left out here. So somehow if I'm looking at 2 boxes times let's say some sigma lambda, I'm saying that this is actually only 1 or 0, and it's 1 if lambda is the complementary tableau, which is this L shape in this case, and it's 0 everywhere else. And this has the consequence that if you give me just any old variety inside the Grassmannian, and you ask me to compute its class in the Chowring, i.e. the coefficients with respect to the basis of Schubert classes, a way to compute it is to just multiply this x with complementary varieties, or varieties that correspond to complementary boxes. So somehow computing these coefficients turns into a geometric problem of intersecting some variety x with a suitable Schubert variety and counting how many points I get in the intersection. Right? So this is the setting I wanted to confer to you. So I get a variety, and I'm playing these intersection games to read off coefficients in this very special nice basis of Schubert classes. So now I will tell you what varieties I want to use to play this game. So I actually get to the topic of the talk. Let's start with a tensor, and this will be a tensor in some A, tensor B, tensor C. Let us presume that it's A concise, so I can basically just treat it as a space of matrices inside B tensor C, just by taking the flattening. And then to any matrix in this space, I can associate a point in some Grassmannian. And if I've chosen bases, I can just view this as I put my matrix in here as a block, and then I add an identity of the corresponding height. And since I've put an identity here, this is a valid point in a Grassmannian. And if I start with a tensor, so a space of matrices, I can just map all of them this way into the Grassmannian, and this will give me some set, which I will call omega t circle, open. And similar to what I did with Schubert varieties, I will now take the closure inside the Grassmannian, and I will call this the generalized Schubert variety associated to T. So this is how I create my objects from tensors. And if you're nervous about the way I said this in bases, do not worry, because there is a way to do this without coordinates. It's basically just taking this matrix, so a homomorphism phi from B to C, and just adding an identity and going into this direct sum, and then I just take the image, and that's all. So my goal is to convince you that these classes, or the coefficients that I then read off as coefficients of Schubert classes in these Chowrings, are nice objects and worthy of study. So maybe the first thing to say would be that these tensors in here, they have this GLA times GLB times GLC action, and we usually don't want to care about this action. We want to treat all of the elements of an orbit as exactly the same. And well, the first sanity check is that this class also doesn't depend on the representative of an orbit. So if I act with GLs on this tensor, I do not change this class. So that's a good first check. And now I would just like to do a somewhat extensive example, and that would be to just look at spaces of 2 by 2 matrices and just characterize for you completely what kind of information is contained in this cohomology class, and hope that this might convince you that these things could be interesting. So let's just do all of the possible spaces of 2 by 2 matrices. So of course, 2 by 2 matrices are 4-dimensional. So I have to look at 0, 1, 2, 3, and 4-dimensional spaces. So 0 and 4-dimensional spaces are not very interesting because a 0-dimensional space ought to always give me just the Schubert variety, which is a point. So I just give the class of a point, whereas the 4-dimensional space should just give me the whole Grassmannian. So nothing interesting to be seen here. It becomes interesting once I use 1-dimensional spaces. So suppose that my space of matrices is just spanned by some generator M, which is non-zero. And so now just based on dimension, I know that the generalized Schubert variety I get should be 1-dimensional. So if you remember back to the Schubert varieties in GR24, there's only one class of dimension 1, which is this. So I just want to read off the coefficient. There's only one number to be found. And to find it, I just have to multiply by the complement and see, that is to say, intersect with the variety corresponding to the complementary tableau and say how many points I get. And to do this, I can, for example, realize that this Schubert variety can be characterized as those points in the Grassmannian where the space has some large intersection with some fixed plane. And I can basically rewrite it as a determinant equation. So somehow, if I say that these two rows, they are supposed to be my unknown point lambda in this omega t, and I say that these two rows with these pij represent some chosen plane, which just parameterizes my Schubert variety that I'm intersecting in, then saying that they have a non-trivial intersection is just saying that they don't span the whole space in this case. So I'm basically looking for this determinant vanishing, where there's one parameter x, which just parameterizes my space of matrices. And I'm looking for the number of solutions to this equation under the assumption that the Pij are chosen generically. So somehow there might be very special planes P, which will give a different result, but there will be an open set of them, which gives me always the same result, and I'm looking for this general result. And if you think about it for a while, I hope you might convince yourself that for generic parameters Pij, when I write out the determinant as a polynomial in X, this will really, should usually have degree 2, or rather the determinant of M. Sorry, the rank of M should be the degree of this polynomial in X, right? Because somehow if I do some kind of Laplace expansion, I will get x squared times determinant of this block M times some scalars, which under this genericity will be non-zero. So in the end, I will get a univariate equation in X whose degree will be the rank of M. And well, under all of these generality assumptions, a polynomial in a single variable has its degree many roots. So I should get rank M many intersections. So I can say that for one-dimensional spaces of matrices, this cohomology class just tells you the rank of this generator. And if you think about it, this shouldn't be very surprising, because I told you the cohomology class only depends on the orbit in the GL action. And it's well known that if I look at a one-dimensional space, that's basically like looking at the generator, and matrices up to this GL action, the orbits they break into just correspond to ranks. So somehow this cohomology class cannot depend on anything else than rank. And it turns out that it actually reads off the rank. So this was the simplest example, maybe. Actually, everything I've said here should work generally. So anytime, in any setting, even in other sizes of matrices, for one-dimensional spaces, the cohomology class just reads off rank. So that's nice. Let's go to 2 by 2 matrices. To two-dimensional spaces. In here, I have two tableaux to consider, two Schubert classes, this vertical and horizontal. I will just do the vertical in detail and tell you that the horizontal is somehow analogous. But let's do this. So for the actual Schubert variety, I can again write some kind of geometric condition. And in this case, it's my lambda just being a subspace of a fixed hyperplane. This is also because this Schubert variety is actually just an embedded copy of a smaller Grassmannian. So I just have subspaces of a smaller space. And I'm intersecting this with a generalized Schubert variety corresponding to a two-dimensional space of matrices. So let's say I choose two generators of this space. And then the condition I'm looking for is that I choose a general hyperplane, so basically a linear form, and then this hyperplane is just the kernel of this linear form. And I just take this element of my space with two parameters, and I'm solving the problem: when does this linear form vanish on the whole space, so on all rows of this matrix? And I skipped some tedious details because, as you can already see, this is getting slightly unwieldy. But if you write it down, you can rearrange it to this non-homogeneous linear system of equations. And again, we're asking, based on what this space spanned by M1 and M2 is, if I take a generic H1 up to H4, how many solutions in X and Y does this have? And I would like to convince you that because of the generality, if this matrix happens to not be full rank, then there will be no solutions. Because somehow, then the possible values of the left-hand side are just some subspace of this two-dimensional vector space. But then there are these other two parameters that are general. So they're picked generally, so they will not hit this smaller subspace. So there's no chance for a solution if this matrix doesn't have full rank, if it's not invertible. So if it is not regular, I get zero solution. So this intersection, this coefficient will just be zero. On the other hand, if it is regular, then I will get one solution because it's a linear system of equations with a regular matrix. So there's always exactly one solution. So now the question is, based on M1 and M2, should I expect that for general H's, this will be a regular matrix or a singular matrix? And again, if I skip some tedium, I can tell you that, well, this can only be generically singular if these two generator matrices had just one-dimensional column spaces, so if they were rank 1, and if in fact these one-dimensional column spaces that they had were the same column space. So all four of these columns were the multiple of, I just lied on a single line in C2. So that's the condition for when I should expect zero solutions, and in all other cases, I should just expect to get a 1. And we can read off some nice algebra off of this, because what does it mean for these two generators to have the same column space? If you think about it, that's just like saying that the actual space they generate, so TA star, is just a right ideal in the algebra of 2 by 2 matrices, and it is also equivalent to this other flattening, TC star, being just one-dimensional. And I should warn, there's about a 50-50 chance that I mixed up my conventions and notations, that this should maybe be a B, but I'm hopeful that this is actually TC star. But the point I would like to highlight is, this means that this cohomology class can tell us something about the multi-rank of this tensor, at least in this particular example. So it knows somehow about some of these tensor invariants that we already cared about. And so now one might hope that if we examine this more generally, this might be a good source of new tensor invariants. So just to finish up, for the horizontal For the horizontal tableau, it goes very analogously. It's just considering row spaces instead of column spaces, left ideals instead of right ideals, and the other flattening being one-dimensional. So overall, I can say for two-dimensional spaces that it's just a linear combination of these two, and the coefficients are 0 or 1, depending on these conditions. Again, nice sanity check. It would be strange if the cohomology class was just 0, but this cannot happen because somehow it would mean that our space of matrices is both a right ideal and a left ideal in the algebra of matrices. And this is very well known that this cannot happen because matrices are a central simple algebra. So they don't have both-sided ideals except for the trivial ones. And so to finish up, actually I will skip the three-dimensional spaces because they're not very illuminating, and also the result is kind of boring because the cohomology class is always just one times this single box. There's actually no information to be read off, sadly. It actually surprised me this first time I saw this because one would expect some kind of symmetry with the one-dimensional case, but alas, it's not happening. So I will be nearing my conclusion. Are there any questions you would like to ask at this point? Yes.
Sorry, maybe I missed something, but initially you were talking about the chowing, and now you're talking about cohomology.
Oh, yes, that was a Freudian slip on my part. Thank you for catching it. Because in this case, the chow ring and the cohomology ring are exactly the same, as they are in most of the basic examples we care about. So thank you. I completely, that slipped my mind. But yeah, there are cohomology classes and chow classes. They're the same thing. Thank you. So to wrap this up, I would like to end on this diagram, which should seem familiar to you because you've seen a version of it already today. I would like to make a connection with what Matej was saying in his talk, because the big picture here is like this. We start with matrices. We map them into the Grassmannian, which means that starting with a tensor, a space of matrices, we can get a subvariety here, and already there we see some nice information on the chow classes. But then one thing that one can do is create a chow quotient of this. This creates what is known as the variety of complete collineations, and it can be interpreted as some blow-up of the projectivization of these original matrices. And in particular, it's a successive blow-up in the locus of singular matrices, of rank full rank -2 matrices, full rank -3, and so on. So somehow this is a generalization of the matroid geometry picture that Matej told you, because how matroids fit into here is that if I were to just take spaces of diagonal matrices, that's the matroid situation. So that's maybe the connection to tensors that Matej was alluding to, because tensors generalize the matroid problem. And so, is there a question? No. So with this picture, I would like to conclude, and thank you for listening with attention. Thank you.